Good day, everyone. I am Jonathan Patricio, and on behalf of my co-authors, let me present our work on zinc oxide-based pseudocapacitors with Electrospun polyvinylidene fluoride polyionic liquid nanofibers, a solid polymer electrolyte. This will be the outline of my presentation. Sustainable energy storage and conversion devices with better performance than current technologies continue to become an active research area globally. Apart from batteries, there have been other energy storage options such as supercapacitors and fuel cells. While batteries provide a significant advantage of high energy density, their limited life cycles, disposal challenges, and charge-discharge management undercut their effectiveness in certain applications. Compared to batteries, supercapacitors have much longer life cycles, yet they have traditionally been challenged by limited DC voltage capabilities and energy density. However, recent advances are improving these issues. Basically, supercapacitors or ultracapacitors are considered to be one of the most promising electrochemical energy storage devices for wearable electronics, hybrid electric vehicles, and for applications that require a burst of energy at a short interval, such as regenerative braking. These ES devices are known to have high power densities, long cycle life, and high Coulombic efficiency of up to 95%. Depending on the charge storage mechanism, a supercapacitor can be further classified into electrochemical double-layer capacitor or EDLC, pseudocapacitors, or a combination of both called hybrid supercapacitors. The ability of a supercapacitor to store energy is highly dependent on its components, which include the electrode, electrolyte, and a separator membrane. Several studies were done to investigate new materials that could enhance the capacitance of supercapacitors. While many researchers have focused on the design and development of novel and high-performance electrode architectures, it is equally important to give attention on electrolytes as they greatly contribute to the device performance. The use of solid polymer electrolytes, or SPEs, for supercapacitors have been extensively studied because they are more stable compared to aqueous, organic, or gel electrolytes. Additionally, SPEs are very flexible and easy to produce. The properties of SPEs, such as electrical conductivity and thermal resistivity, can be enhanced further by processes such as graft copolymerization, plasma treatment, and by blending with other polymers. In our previous works, we have demonstrated that ionic liquids as solvent-free electrolytes have shown promising electrochemical advantage over organic and aqueous electrolytes due to their low flammability, non-volatility, high ionic conductivity, and wide potential window. Similar to those reported in literatures, the rheological and electrochemical properties of these ILs can be tuned such that the alkyl chain length and the choice of an ion have an effect on the viscosity and on the capacitance of the supercapacitor. Certain ILs, depending on the structure of its alkyl group, can be polymerized, making them amenable for blending with other polymers. Polyionic liquid offers mechanical durability, low glass transition temperature, and high ionic conductivity even in the absence of organic solvents, thus making them appropriate to undergo electrospinning. On the other hand, polyvinylidene fluoride, or PVDF, is known to be a piezoelectric polymer that has been used in several applications due to its mechanical integrity. The incorporation of PIL to PVDF is expected to provide a synergistic effect on the properties of electrospun fibers, suitable to act as solid polymer electrolyte for supercapacitors. In this study, PVDF PAL composite nanofibers were utilized as solid polymer electrolyte separator membrane for zinc oxide-based pseudocapacitors. The synthesis, structural, and microstructural properties of the PAL and its composites with PVDF will be presented, and the feasibility of utilizing the Electrospun composite nanofibers and the effect of PAL concentration on the electrochemical performance of the fabricated pseudocapacitor will be discussed. To carry out our objectives, a two-step synthesis was employed to prepare the target PIL. The ionic liquid monomer was obtained through a solventless monochemical synthesis that involves direct quaternization reaction between N-vinyl imidazole and N-bromohexane. The reaction occurs via SN2 mechanism with the conversion of tertiary amine to a quaternary ammonium salt through the alkylating agent N-bromohexane proceeds through a bimolecular nucleophilic substitution. Meanwhile, the synthesis of PAL was done through free radical polymerization initiated by AIDN that was purged under nitrogen atmosphere. The free radical polymerization was employed because it often yields polymers with controlled molecular weights. The final products obtained have 93 and 62% yields and were characterized to confirm the structures. For the electrospinning of the composite fibers, polymer solutions of 7% PVDF mixed with a varying PIL concentration in dimethylformamide were prepared. A 5 ml sample for each solution was electrospun using these deposition parameters. And the electrospun nanofibers were then characterized using available techniques. For the results, the proton NMR spectrum is shown. Here, the presence of an upfield signal at 4.20 ppm indicates a successful attachment of the hexyl chain to the nitrogen of the imidazolium ring. This is because of the formation of a quaternary ammonium salt from the reaction of N-vinyl imidazole and the N-bromohexane. This was further validated by the carbon NMR spectrum in which an upfield signal at 50 ppm was observed and was assigned to the carbon of the hexyl chain attached to the imidazolium ring. The presence of downfield signals at 124 ppm, 130, and 136 ppm were due to the aromatic carbons of the imidazolium ring. Similarly, the proton spectrum of the polyionic liquid confirmed its polymerization as depicted by the broadening of the signals typical for polymers. In addition, the two doublet peaks at around 5 to 6 ppm of the IL disappeared. This disappearance of vinyl signals suggests that the vinylic protons were converted to the polymeric backbone of the polyionic liquid and had a new chemical shift at around 1.81 to 3.14 ppm. This was also verified by carbon NMR spectrum in which the signals at 109 to 120 ppm of the IL have shifted to 50 to 67 ppm for the polyionic liquid due to the conversion of the carbon-carbon double bond to carbon-carbon single bond, suggesting the successful polymerization of the ionic liquid. The downmost field signals were then still assigned to the carbons of the imidazolium ring, and the rest of the peaks were for the carbons of the alkyl chain bonded to the ring. The FTIR spectra of the synthesized IL monomer and PIL were obtained using attenuated total reflectance technique with transmittance mode. Looking at the FTIR spectrum of the ionic liquid, it can be observed that the CN stretch was found corresponding to the functional group present in the imidazolium ring. The presence of CN stretch at around 1168 per centimeter confirmed the quaternarization of the alkyl chain of the imidazolium ring. Meanwhile, for the PIL, a decrease in the intensity of the bands associated to carbon-carbon double bond and CH stretch was observed due to the conversion of the vital carbon-carbon double bond to the polymeric backbone of the polyionic liquid. Nonetheless, these bands were still present due to the presence of carbon-carbon double bond in the imidazolium ring. The appearance of all expected functional groups sufficiently confirmed the synthesis of the target ionic liquid monomer in the polyionic liquid. The incorporation of the PIL to PVDF was verified using FTIR spectroscopy. As shown in this figure, transmittance bands from the PL, such as the OH stretch and the CH stretch, can also be found in the spectra of the PVDF PIL nanofibers. It can be seen that intense bands at 839 per centimeter and 1277 per centimeter suggest that the PVDF is in its beta phase, indicating that the nanofibers have strong electrical properties. Now, the scanning electron micrographs of the PVDF-PIL composite nanofibers were obtained to examine their morphology. From these images, the mean diameter was determined and the corresponding histograms show the distribution of the fiber diameters. It is apparent that increasing the PL concentration added to the PVDF solutions resulted in an increase in the fiber diameter. Nanofibers with smaller diameters would yield a more oriented structure, leading to an improved mechanical strength and more precise diffusion paths to facilitate ion mobility. The wettability of the electrospun nanofibers was studied using sessile draft method. The generated contact angle images presented an increase in the water contact angle as the PIL concentration increases. This is due to the hydrophobic nature of both the PVDF and PIL. A hydrophobic polymer separator membrane is more suitable for supercapacitor applications because the presence of trace water or moisture could constrict the electrochemical stability window of the electrolyte, hence suppressing the energy density of the device. Now, for the electrochemical analysis, the cyclic voltammograms of the zinc oxide-based pseudocapacitor prototypes were obtained to investigate its charge storage and evaluate its electrochemical performance. Interestingly, when configured in a positive bias between 0 to 0.5 volts, quasi-rectangular curves were obtained with no Faraday peaks at any point in the voltammograms, indicating that the charge storage process was reversible, primarily attributed to the electrostatic interaction typical for LEDs. From these voltammograms, the calculated aerial capacitance was found to increase with increasing PIL concentration. This may be due to the enhanced mobility of ions contributed by the PIL moiety. In addition, as shown in the atomic force micrographs, the use of deposited zinc oxide microstructures as electrode material may have afforded a better surface-controlled kinetics of charge carriers due to its relatively high surface area. It is noteworthy that the capacitance of a supercapacitor is dependent on the surface area of the electrode material and its interaction with the ions in the electrolyte. To summarize, polymerized ionic liquid based on poly-1-hexyl-3-vinyl-imidazolium bromide was synthesized using a two-step process. The morphological and surface properties of the Electrospun composite nanofibers were studied. Results showed that a significant increase in fiber diameter and hydrophobicity was observed as the PIL concentration increases. The fabricated pseudocapacitor prototypes was made by mechanically pressing the Electrospun composite nanofibers between two electrodeposited zinc oxide-based electrodes with ITO glass as a current collector. Aerial capacitance values were acquired for the prototypes containing varied percent loading of the PIL. These measurements were determined using cyclic voltammetry, in which the aerial capacitance values increase as the PIL concentration increases. These are our references. We would like to acknowledge the Department of Science and Technology, Philippine Council for Industry, Energy, and Emerging Technology Research and Development, and the University of the Philippines Diliman Natural Sciences Research Institute for funding our study. That would be all. Thank you for your kind attention.